Good morning, dear students. Welcome to another session of microwave and antennas. So, in previous session, we discussed regarding reflection coefficient, and we solved a problem related to the transmission line equations. So, moving forward, we are left with another one parameter to be discussed, that is transmission line coefficient. So, yesterday we discussed regarding reflection coefficient derivation, what is meant by reflection coefficient, and derivation of reflection coefficient, in which we represent reflection coefficient in terms of a load impedance and characteristic impedance. So that is what we have discussed in the previous session. So the final equation what we had obtained was reflection coefficient is equal to ZL minus Z0 divided by ZL plus Z0. So this was the final equation what we have obtained. So now next we have to look forward with the transmission coefficient. So what is meant by transmission coefficient? So here we have transmission coefficient, which is basically defined as the ratio of the transmitted voltage to the incident voltage. So reflection coefficient is ratio of reflected voltage to the incident voltage, whereas transmission coefficient is related to the transmitted voltage to the incident voltage. So in this case, if I represent the transmitted voltage as Vt and incident voltage as Vi or V plus, so then this is the transmission coefficient representation. Now we can also give the transmission coefficient in terms of current. It is again equal to the ratio of the transmitted current to the incident current. Now it is almost similar to the previous derivation what we had done, but what is the transmitted voltage or transmitted current? So now in this case, if you consider this representation over here, if you consider this parameter over here, if you observe at the generator end, we have the overall transmitted voltage. We have the overall transmitted voltage. So which when it reaches the load, it will be divided into incident voltage and reflected voltage based on the load parameter. So if we consider that, what happens is this transmitted voltage is equivalent to the incident voltage plus the reflected voltage. So it is equal to these two parameters. So that is what they have represented over here. So the transmitted voltage is equal to the incident voltage plus the reflected voltage. Therefore, when I replace the equation for the transmission coefficient, there I'll be getting it as Vi plus Vr, which is incident plus reflected, divided by the incident voltage. Now, what is Vi and Vr? So we had obtained in yesterday's representation. So instead of that, we can just take out the numerator in common with each of the parameters. So Vi by Vi will give you 1, and Vi by Vr is the other parameter. Now what is actually this parameter? Vr is the reflected voltage to the divided by the incident voltage. This is actually equivalent to what? The reflection coefficient. It is equal to reflection coefficient. Sometimes it is noted with K also. They'll be representing it with K. In some books it will be rho. So it depends on these notations. So therefore I can write this representation, that is the transmission coefficient, as equal to 1 plus the reflection coefficient. Now, but what is reflection coefficient in terms of ZL and Z0? it is actually equal to ZL minus Z naught divided by ZL plus Z naught. So when I substitute this entire equation and simplify it, I'll be getting the transmission coefficient equivalent to 2 times ZL divided by ZL plus Z naught. 2 times ZL divided by Z naught. So this is the derivation for the reflection coefficient. So next parameter which comes in play is the voltage standing wave ratio. So why does the standing wave ratio come into existence? Now here if we observe, what we have is you are having an incident parameter and you are having a reflected parameter. So we'll be having incident voltage, incident current, reflected voltage, and reflected current. So this will be associated with the incident wave and a wave which has been, say, reflected back. So because of these two parameters, what happens is in the transmission lines, we'll be having the standing waves which are being formed. So we'll be having something called as standing waves which are being formed. So for example, if I have say something in this transmission line, I'll just represent in analogical form. So we have a wave which is traveling from the from the source end to the load end. Now at load, say if there is a mismatch, what happens is depending on the type of load, there will be different the same possibilities over here. Now if I assume that this wave say exactly it gets terminated here, and what happens is this entire wave is reflected back. So what happens is this will be reflected back. Now in this case what happens is because of this incident wave is still present, and this reflected this thing is also present. Now what happens is they two interact with each other, that is the incident wave and the reflected wave both interact with each other. So when they interact with each other, they form what we call as the standing waves in the transmission lines. So when we have transmission lines, right, we have a few other parameters over here. That is, so I have incident, I have say the reflected parameter. So here what happens is if we measure some points along these transmission lines, what happens is this reflected wave will be having maximum at certain points. That is, the voltage is maximum at certain points. So here it is in between. So this might be the minimum voltage. This might be the minimum voltage. So we'll be having 3-4 parameters. That is, one is the maximum voltage parameter. One is the maximum voltage parameter, and say another one important parameter is the minimum parameter. So we can have Vmax and Vmin. So if I take the current rate, it will be in opposite this thing. So at this point, I'll be getting I minimum, and here I'll be getting the I max. That is, the wave will be in the opposite form. So at present, here we'll be having the voltage maximum, and here we'll be having the voltage minimum. So these two parameters become important for us when we discuss regarding uh, the standing waves. So now what is meant by voltage standing wave ratio? SWR is nothing but standing wave ratio. So this is a standing wave. Sometimes we represent it as SW, and if you have to represent ratio, right, we write it as standing wave ratio. In short, we write it as SWR. Now, when we consider the voltage parameter, we get what is known as voltage standing wave ratio. So which is basically formed because of the incident and the reflected waves, because of the incident and the reflected waves which are present in the transmission lines. Now what happens due to this incident and reflected waves, we get what we know as standing waves. And if you're considering the voltage standing waves, right, in that we'll be having positions at which along the transmission line, we'll be having a maximum point and the minimum point of the voltage. That is what I discussed previously. So this is how it appears. So when we try to measure, we'll be having a maximum at this point, and when we try to measure the minimum, we'll be having a voltage minimum at this point. So this is what we'll be having when we consider the voltage standing wave ratio. Now another point to note down here is, now if I consider any wave, say for example, if I consider this wave from this point to this point, this entire thing is how much? It is equal to wavelength. It is equal to wavelength of the wave. So similarly, if I consider at any point, so Vmax to Vmax, that is a distance between two crest is what? This is also lambda. Now here, if there is another minimum, we'll just consider if there is a minimum over here, the distance between two minima, we call it as minima or maxima, is also equal to lambda. So here, what we are trying to specify is when we have a wave, and we have two maxima points. So distance between successive maxima is equal to wavelength, and distance between successive minima is equal to its wavelength. Now, when we consider this, right, if you just observe distance between a successive a maxima and its successive minima, that is distance between these two, will be equal to what? It will be equal to half of the wavelength. Distance between distance between a maxima and its successive minima is always equal to lambda by 2. So these are a few points what we have to look out when we are discussing related to these parameters. Now this is in case of this wave. But what happens is, since I showed you the other waveform, right, we have incident and reflected parameter. So what we have, say we have an incident parameter, and say we have a reflected parameter over here. Now let us consider, so when we have this, then only we have voltage standing wave information. When we have this, then only we have this information. Now previous discussion what I did was in general in terms of a wave. It was a wave. So distance between two crests or the maximum points is lambda. Distance between two minima or the troughs is lambda, and distance between a crest and a trough is lambda by 2. Now this is in general when we consider the waveform, and the distance between a crest and a trough is lambda by 2. Now when we apply this concept to the voltage standing wave, here we are specifying that it is lambda by 2. So this is with respect to the incident wave, which is having a wavelength of lambda. We have a wave which is being generated by the generator, and this is with respect to the incident wave, and its wavelength is lambda. So with respect to this, we are representing this parameter. Now how is this lambda by 2? Now here it will appear that it is lambda, but here what they have done is they have actually specified in this form. It should be having in this case, you should have included this one. Okay, so now we'll not bother about that. So we'll discuss regarding this parameter. So what we have, say we have an incident wave. Say we have an incident wave, and we have a reflected parameter. So either of one you consider as incident, and the either of the other you consider as the reflected parameter. So when say we are having representation in this form, so this is giving you the voltage standing wave. So now here you can see that you have what all parameters. You have parameters. There is a maximum at this point. 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 So these are called as voltage maxima, or sometimes voltage maximum for the standing wave. Then you have a minima over here. We call it as a minima or a voltage minima if it is related to the voltage parameter. So these are called the voltage maxima points. These are called the voltage minima points. Remember, lambda is associated with the incident wave, that is the wave which is being generated by the generator at the generator end. That is this one. So with respect to this, I have to identify these parameters. So in this case, what we have, we can see few things. So this is a max point Vmax, and this is another Vmax point. So if you consider, say, this wave over here, if you consider this point, so distance between this point and this maxima is equal to what? It is equal to lambda. So in between you are leaving one point. So from this point to this point, it is actually equal to lambda. So when we consider the distance between the successive maximas, when we consider the distance between the successive maximas, so it will be what? So it will be say from this point, if I consider this point, distance between the successive maxima. So this will be half of this one. It will be lambda by 2. It will be lambda by 2. So this diagram, what they wanted to represent is actually with respect to another waveform which has to come over here. It is actually distance between these two. Okay. So here we have distance between two maxima points is lambda by 2. Similarly, we have another parameter over here. Say if I consider these three points, minima. So here what I have, distance between this minima and this minima. That is, I am leaving in between one. So that is alternate value of minima. So this parameter is actually equal to lambda. Distance between successive minimas. Distance between successive minimas is what? Successive minimas is lambda by 2, half of this one. So distance between two successive minimas is lambda by 2. So remember, distance between two successive maxima is equal to lambda by 2, and distance between two successive minimas is also equal to lambda by 2. Now what about the distance between a maxima and a minima? What about the distance between a maxima and a minima? So here you can see that we are having a minima point here, and we are having a maxima point here. So when we have that, if I have to measure this, this turns out to be lambda by 4. Distance between a maxima and a successive minima. So if I continue and if I have another minima over here, distance between those two also will be equal to lambda by 4. So we have 4 parameters. That is distance between two successive maxima is lambda by 2. Distance between two successive minima is lambda by 2, and distance between a maxima and its successive minima is lambda by 4. So these are the parameters related to the maxima and minima in a voltage standing wave. We have the VSWR measurement, in which we have Vmax and Vmin, which we represent it as Vi plus Vr divided by Vi minus Vr. So in this case, when I take say Vi common, so what I'll be having is Vi gets cancelled. When I take Vi common, Vi gets cancelled, and we have 1 plus Vr divided by Vi, and divided by 1 minus Vr divided by Vi. But what is Vr divided by Vi? That is the reflected voltage divided by the incident voltage. It is nothing but the reflection coefficient. Therefore, VSWR can be represented in terms of reflection coefficient, which is given by 1 plus reflection coefficient divided by 1 minus the reflection coefficient. Now, if you want to represent this in terms of the transmission coefficient, so in previous this thing we discussed what is transmission coefficient. Transmission coefficient is given by T, or tau is equal to 2 times ZL divided by Z naught, and it is equivalent to 1 plus the reflection coefficient. So if they ask you to represent VSWR in terms of the transmission coefficient, we can substitute the representation for the reflection coefficient in terms of the transmission coefficient and obtain the result. Okay. So these are the derivations which are related to these things. So any query from your end? Any query from your end?
No, sir.
No, sir.
I had just missed out this part, so you can just consider this. I had missed out this one. Okay. Okay. Now, in terms of ZL and Z0 also, we can obtain what is VSWR. So what you do is you take 1 plus the representation for this one, that is ZL minus Z0 divided by ZL plus Z0. So in denominator also you replace that parameter. So when you replace that parameter and simplify it, you will get equation in terms of ZL and Z0. So here, what is the range of the reflection coefficient? What is the range of the reflection coefficient? Range of the VSWR. Now we know that what is the range of reflection coefficient? It is in the range of 0 to 1. It is in the range of 0 to 1. So if I substitute 0 over here, if I substitute 0 over here, so what I'll be getting? VSWR, say I'll represent it as V, VSWR will be equal to 1. And if I substitute the reflection coefficient is equal to 1 in this equation, what I'll be getting? I'll be getting it equal to 1 minus 1 is 0. So anything divided by 0 is what? Infinity. It is infinity. So here we have VSWR is in the range of 1 to infinity. We have VSWR in the range of 1 to infinity. So this is what we have in this case. Okay. Remember, 0 lesser equal to rho, that is reflection coefficient, is lesser equal to 1. VSWR is in the range of 1 lesser equal to, say, VSWR less than infinity. Less than infinity. So this is the range of the voltage standing wave ratio. Now for when we consider any of the loads, right? Load is nothing but the impedance what we are considering over here. Say in this network, right? So when we are considering these parameters, right, we have a load over here. So depending on this load, either you can have VSWR in the range of 1 to infinity. Now, what does infinity in a practical situation imply is infinity is nothing but a very high value of VSWR. Say in some conditions, I might consider say 10 as a very high value for VSWR, or 100 might be a very high value. So this values I can consider it as infinity in your practical situations. But it is a very high value. That is what we try to intend. So theoretically, we have it in the range of 1 to infinity. We have it in the range of 1 to infinity. So this is what we are having for these cases. So now just a recap of all the equations, what we have discussed up to this point. We have characteristic impedance. We have the characteristic impedance, which is given by Z0, which is equal to square root of Z by Y. Remember, Z is equal to R plus J omega L, and Y is equal to G plus J omega C, and where omega is 2 pi F, and F is the operating frequency what they have specified. So next you have the propagation constant. You have the propagation constant, which is given by square root of Z into Y. Then gamma itself is equal to alpha plus j beta. When you solve this equation, right, for gamma, you'll be able to separate the real and imaginary parts, which will give you the alpha and beta values respectively. And remember, alpha is in terms of Napier's per meter and beta is in the terms of radians per meter. Beta is also given by what? Beta is also given by 2 pi by lambda, where lambda is the wavelength of the wavelength on which the transmission line is operating. So reflection coefficient we discussed, in which reflection coefficient in terms of ZL and Z0, it is given by ZL minus Z0 divided by ZL plus Z0. And VSWR is given in with respect to the reflection coefficient, which is equal to 1 plus reflection coefficient divided by 1 minus the reflection coefficient. Now, if you want this equation to be represented in terms of say ZL and Z0, just substitute this reflection coefficient with this equation. Simplify the equation and you will obtain VSWR in terms of ZL and Z0. And here, remember, we have to consider the magnitude. We have to consider the magnitude over here. Then for lossless lines, you have to substitute R and G equal to 0 in the previous equations, and we'll be getting all those parameters. And remember, this is also required in your case. If you have to use the old calculators, right? Then if angle 1 is divided by angle 2, the overall angle is given by the difference between those two angles. That is this theta 1, the numerator angle minus the denominator angle. And if you're multiplying two angles, say you have some equation in this form. There is R1 theta 1 multiplied with R2 theta 2. So if this is the case, the overall result will be R1 into R2, and angle will be added. It will be theta 1 plus theta 2. It will be theta 1 plus theta 2. And this one yesterday we had used. If you are taking a square root of an angle, so this angle will be given by theta into whatever this factor you are considering. So here it is theta raised to half. So the overall angle will be theta divided by the 2. That is theta into 1 by 2. It will be equal to this parameter. So since you are doing complex problems, right, you should take care of these things. This problem had we taken